Welcome everyone for Cloud Computing and Big Data. Today we have our short lecture 15. And this lecture is about big data streaming, a very big area which has lots of tools, lots of applications. Essentially, when the streams are getting so big that you can actually not really store all the kind of information that comes in, and you basically have maybe provide some filters to really get out of this large stream of quantities of data really something out and something useful out. So we will discuss this topic, although it's really a short lecture, because this topic is really big and could fill easily a whole course of different approaches to different open source tools which are available, and the relevance it has today because we have an exponential growth of data. That means our archives are running full and we're really having a hard time to store every single bits of information we have. So chances are in the future, we have much more streaming tools readily available to also think about what we not need to store. But before we go into the materials of this lecture today, let us review what we had the last time. The last time we basically had another short lecture 14 with a equally rich information about online social networking, graph databases. All of those topics could be easily filling another lecture or course, basically, if you want, especially graph theory, graph traversal, the structures of graph, the performance of graph, as a topic which is very rich, which basically can easily fill a whole university course. And I'm not the expert in that, but what I wanted to convey basically in the short lecture 14 the last time was that cloud computing has lots of these applications. And we also took away the message that in a way, these online social networks are really a good example how you can leverage graph databases. And firstly, the idea of online social networks is very well, I think, captured by the idea of different users or creating different content. So in a way, the data centers accumulating data basically for specific of these applications very significantly in terms of big data. But if you zoom in, so to speak, in this large applications of online social networks compared to maybe other traditional applications, you will see really a very inhomogeneous and unstructured way of storing information, because some people use Facebook more than others. Others like to have lots of video shared, while others just share a little bit of text, and others just basically register to see basically the others. So this is a very interesting topic because it grows in a way that is unpredictable, if you want. And the best way to target this and to basically get information out of this and to basically use this information in real time, that's a very important factor we discussed the last time. We want to see the like of a Facebook user now, not in 10 hours or tomorrow in 24 hours. So we want to have a real life experience and in real time on all of these different users. And if you think about getting to billions of users, where Twitter maybe has just a couple of millions of users, getting to billions of users with Facebook and so on, of course, that's a different challenge. And in order to tackle this challenge, we learned last time that Facebook manages in a way of having a graph representation of their online social network, with having the nodes as individuals or organizations, and then, of course, all their relationships that we have between all of these different entities, as we will call them. So in a way, you see these kind of inhomogeneous growth again represented in this, let's say, interesting unstructured graph with lots of different connections. And it's not a one-to-one connection here in this mesh. It's rather very inhomogeneous, totally unstructured, depending on the person's profile, on the organization's profile, and so forth. So in this sense, the Facebook engineering people have basically described a little bit how they do it with a Tau graph database. And the way to better understand this is basically this interesting graphic that we had the last time. You would say nodes can be users, but also, of course, nodes can be a comment or a specific event, like a check-in to some specific location, which might be then the Golden Gate Bridge. So you have interesting entities, as we call them, which are quite important and represent, so to speak, the nodes of this graph that you see a little bit here in an abstract representation. But then, of course, the relationship matter, right? And here you see basically the friend of a friend can be then easily transverse this graph traversal techniques. And basically, of course, This is a very unstructured way. You see here the like, the authored by, tagged, different relationships really that then bind these different nodes together in a kind of consistent story that is basically real and of course also should perform in real time. And this is possible with graph databases, but we also learned with some different areas within Facebook, like HBase, we learned in previous lectures, some indexes and some other information is actually used with NoSQL data stores like HBase, or other information is even combined with SQL data stores. So the long story short is, if you look on the old social networks, it is basically a smart combination of different databases, whereby basically the graph database is a very, very particular one, but still there are lots of other databases that help to really get to the good performance that we know from Facebook, from YouTube, from Twitter, and so on. So the other way I wanted to convey basically the last time were two different things. That firstly, you would say online social networks give you free access often, but this free access, of course, has a particular purpose of maybe getting you exposed to much more advertising as you want. You will very well know, basically, if you are in YouTube and you're not YouTube Premium, you will get lots of advertising along the way. Same is for Facebook. On the right side, basically on Facebook, you will see this different advertising. So Google Ads, Google AdSense, this is a big topic. You can use this for search engine optimization of your own website, but you can also put specific ads that you basically put in Google AdSense on your different web pages, basically, and have space for it, although you never know really who will be there. You basically just give the space on your web page to Google AdSense, and then there will be some marketing coming basically that fits basically to the page idea. Like here in the big data tips, you see, of course, marketing is put in there, which actually reflects a little bit the text and a little bit the purpose of the website. And that's what you want. We call it targeted marketing, right? So basically that is really customers that are interested in the ad, and not, you know, having now suddenly something like a lawyer or flowers or whatever marketing for a very tech IT website. So this is possible today very easily for Facebook, for Google, to really have your audience reach in a very particular way, all one credit card swipe away. You can control the budget. You can have the age groups. You have different ways how you basically create your audience here. You can have locations only in English-speaking countries, ages, whatever it is. So a very lucrative business, not only actually for Google and basically for Facebook today. You will also find companies today that are basically focused around the term called SEO, the search engine optimization profile, which really helps you with marketing, with online marketing, not only improving the website ranking in basically search engines, what this is alluding to, but also optimizing a lot of different social media aspects. And the keyword planner is a tool I would suggest to you if you do websites. Look at that, understand a bit of it from Google Ads and the keyword planner tool, what people are really searching for. And then you basically can do a much better maybe title of your web page in terms of posts, or better title in terms of YouTube videos. So a very interesting topic. Again, we didn't have enough time for it. We would cover a whole course usually on that. And trainings are especially also in the ad domain. So let us come today to the topic of streaming. So big data streaming is equally another interesting lecture in more ways than one. Firstly, because it's also our last real content lecture. So congratulations if you pass this one. We basically are finished with the course, as we should be, because it's our last week together. And then basically we'll go to the epilogue, which covers more job profiles, the view of the course from another perspective. But today is really the last content around big data streaming. And also there, I could talk hell a lot in terms of different cloud services like AWS Kinesis, for example, or basically the Apache Spark streaming library that, of course, in terms of graph or machine learning libraries that you already know for Spark, you can also twist the whole idea of working with data to streaming. And we will talk about it. And also why basically the idea of data streams is now so important these days, enabling perhaps also what we call interactive access, visual analytics on real-time data to really understand the data and maybe filter out some data with interceptors that we also will learn a little bit in this course. needless to say, there are lots of open source tools available. So Apache Spark has a streaming library. We have Apache Storm, we have Apache Flink, a more in-memory approach. And you can combine this with Kafka. There are basically no limits. That's why I say this topic has huge potential to be basically a future-oriented course also completely as a whole university lecture series. But here in this course, we just provided as a short lecture, giving you some pointers for what basically you could study if you're interested in these topics, and really connected a little bit back to the machine learning experience, especially if you think about online learning. So let's come back a little bit to the idea of what are data streams. So basically here we talk about web actions that could be data streams. So every time you like something, we have learned about the measurement data in terms of different streams from sensors. Basically here you see the square kilometer array with measured data sets. And of course, you could also think about having a large simulation on HPC executed, running perhaps the weather forecast, or as you see here in astrophysics application I was involved with once, basically simulating galaxies and so on. So all of these are different data streams and have a different, let's say, source, but all of them have in common that the data is constantly created on the fly, so to speak, and basically leads to some, let's say, sync, where you basically have then some information you want to look, perhaps some statistics on your website. For the measurement device, you maybe want to perform some machine learning, some prediction of some measurement data. And then from the computational simulation, you want to see some effects, like, for instance, having a black hole in the galaxy moved here and there. And all of them have in common that it makes sense to think about so-called optional filters. So you may be just interested in some of the web actions, not all of them. The measurement device data is maybe very rich and you will focus just on one specific part of the measurement types. Or the computational simulation could have also very many facets. If you think about different weather forecasts, you may be just interested in precipitation, like rain and so on. So there are different ways how you now handle these data streams, but basically the fundamental architecture of these data streams is basically looked here. But then what the stream entails and where the real information is that you see here a little bit, symbolized with the red thing, is something you're mostly interested in, but it's also not so easy to always know, because a stream can have lots of other information and you have to pick the right information on time, where filters might be actually quite useful. Then new types really of data streams these days are basically the following, called in an example called crowdsourcing. Perhaps you have heard from it, that usual citizen scientists or usual citizens are used to be involved in science that are basically not really, scientific, or don't have really, let's say, the scientific background, but can help, or let's say, for instance, do lots of photos in jungles or in, let's say, interesting parts of the earth where scientists usually are not always are. And unless you do a, hobbyist, which might be the next category, where you say there's a couple of those out of these that create then data sets in the petabytes, contrast to citizen scientists that have the potential to create easily exabytes, because there are just so many, perhaps, where only a few of them maybe would pick a specific domain, let's say like the flowers we have had in the beginning of the course, as a domain of a hobby, and then do lots of photos of Iris virginicas and Iris vitosas and so on. Of course, there it's where you start to have a bit of trust, because it's a hobbyist or a hobby guy that is basically, or lady that is basically having a very specific topic, so know already something about the topic. Otherwise, you would probably not having it as a domain, as a hobby. So basically, this can contribute to petabytes of data, where the word of trust is also something that we like to be talked about when we have data science, because we can imagine that citizen scientists just put some data online where we don't really have a full trust on it. There's no expert behind it. A hobby person is getting into, let's say, the domain, knows a bit more about it, and there we have usually more moderate trust. And then, of course, when you think about the people that do really as experts, let's say photos, videos, or whatever, as an example for data streams, there you basically have a very high trust. But of course, there aren't that many. So here we talk about, again, of terabytes. And this puts into perspective the idea of how basically clouds are exposed now to the content that is uploaded on several sites. So you would say exabytes is tough, but of course, we basically would focus rather on the domain scientists with their high trust. But of course, this is valuable data. So, I mean, basically, we don't have so many domain experts usually. So having all access to this data is useful. But of course, when you analyze it, you always have to think about where the origin is, where the data source is, and who was giving rise to the data in terms of noise and so on. And it could originate from many different computing devices. I mean, today it's very clear that could be handheld devices, but also desktops, cameras, high resolution, specified objectives in terms of kind of very specific photographs that you can do, whatever it is. But it leads to the challenge still of this quality control I was alluding to. So here it's basically getting the trust in the data, which is very important. If you want to do machine learning, if you want to do data sciences with it, it's important that you are sure that there's a high quality of the data. There are certain correlations or validations that you can do with different data sets. There's basically outlier detection, outlier correction, some statistical data mining method that can help to really analyze a data stream and think about, are there outliers? Are there measurement errors that point to something which is unusual in the data? So this is a real big problem sometimes, especially also in data streams, where you have an error-prone measurement. You think about basically a measurement device that is gone wrong or is wrongly configured. And then basically to the high velocity of data streams over the time, it's basically could be hard to detect or even to correct it because the stream is ongoing. Let's say you have a buoy somewhere in the ocean and there's more and more wildlife living on it, like, you know, kind of small creatures maybe on the sea, where you have a measurement device maybe below water sometimes. This is a real world scenario. So these are all different challenges where we have to look at when we think about data streams. So looking on the way how you would identify data leads us to another challenge in the data. Because we have a time series, if you want, this is here what you see a little bit here, right? With each timestamp, there comes new data measured. It could be maybe from this big instrument that we say here as an example. But we have here the understanding of basically thinking about how we can actually have some of these data streams really made somehow referenceable. So if you want to say, this is a measurement time series that I really, you know, measured with my measurement device in this year, so how I reference it, right? Because it's having unique pointers in time, different measurement values in time. There, basically, you want to basically maybe permanently store a subset of this stream and then make it referenceable, that you see here a little bit also on the left example in a publication where you say, this is my studies in Indonesia, etc., on this particular time. And this is something the domain called persistent identifiers. So this is something where we talked a little bit about in the EOS Build to Share service, where we said every data item that you upload, which you can use with this data streams, for instance, should get a persistent identifier, so you can always reference it. But of course, what is when there's an unfinished, you know, data set, or basically what is if you want to add missing values later? So there you are a little bit in trouble, because we said also the PID will be assigned to a complete data set and not something which is basically still in measurement or so. Hence, for data streaming, it's a little bit different, because in a way we kind of expect that data is still coming in while you work with it, while the data set is unfinished. Quite different from the machine learning data sets we already looked at, like the MNIST data set, right? Very static, character recognition, 60,000 images. It's there. It's basically not changing anymore. We can work with it basically offline, and it's nice. Here we're talking more about online data generation all the time, and we have to work with it. And to reference that is basically quite a challenge. Now, what one of the future items is, and what people have already started in the last decade, basically is to work with the data streams in two different directions. So We call this a little bit like real-time analytics, where you think about that a stream has always one direction, right? Basically, and thinking, okay, the source is always, of course, putting data to the thing. That's why we call it a data stream. Could be, let's say, logs, could be measured data, as we know. But what if there's a second, so to speak, line, which is more a sort of command line, or basically a kind of steering the data stream a little bit? You could imagine in the data stream there's hidden logs here in files. You can change some parameters of the web application and then basically have different streams coming back. You know this a little bit from YouTube when you click on the video timeline, right? Then you have the measurement device. Also there, the data stream is measured data, might be something to think about. So you basically can have different angles, right? Different resolution perhaps in your measurement device that you can steer, which basically then influence what data comes out of the data stream, right? So in the next time step, the data stream will basically have different data coming out because you change some resolution. And you can go on and go on. Like here, you see, for instance, an example where you see the galaxy happily and nicely going around this black hole here or this other planet. The gravity is basically here computed, the interactions of stars in an n-body simulation. But of course, what you can do is always add and remove some of the locations of this particle. So you can basically drag this black hole here into the stars, and you will see that the whole simulation basically will significantly change because you changed essentially the physical setup of the data stream. So hence, this is another way how to deal with this information. You want to put the pointer on interesting situations. You want to analyze the data as you speak in real time. And this is in quite contrast to the best idea of just having data streams all the time basically generated and you can't influence them. But technically, of course, this also represents a challenge because you have to create another channel, so to speak, which is a steering channel, a command channel to basically these different sources, which could be not so trivial if you think about large-scale devices. Now, when you want to work with the streaming, data sets, there are different open source tools I already was saying before, which could be relevant. One of them is, of course, something indirectly you know already. It's the Apache Spark streaming library. So here we're talking about basically having the same idea of Apache Spark that you already know from the MLlib and also more recently from the graphics that I was alluding to before. Now there's a whole package and API around streaming. And this also works particularly nice because it has the same look and feel that we already know from previous lectures working with Python, and very compact. You can actually here have, for instance, a Twitter tweet organized, looking at, and then basically think about the text that only contains Spark as an example, or your company name, and it will be basically then filtered by this particular one. That's how you basically find it. And the interesting thing is, of course, as you know, Spark is quite robust and stable. That's why we basically think about it as being also able to survive node crashes that you have here at certain point in times, where you basically can live with it because you have also this parallel infrastructure that we already created with Spark and the different worker nodes and so forth. So in a way, you basically can, have different filters, basically looking through. Here's a word count example, where you basically, every time when there's a word, you of course can basically increase the word count or whatever it is to really do, and then basically work on the streaming data. So especially this lost work is something where you can think with the speed of this tweets today, for instance, this is quite handy to actually work with this in order to analyze really the whole text, even if there are errors on the way. Usually Spark is able to resubmit the jobs if there's something happening. So very powerful. And of course, it's inherently has the scalability designed. As you know from the beginning of the course, when we start with Apache Spark in MS Azure or so, we had the scalability in line. We just define more workers, basically. And with this, we can digest much more bigger data streams. It works the same way, basically, here with the streaming data. Swipe the credit card, create more workers. Of course, you know the game with Spark from the beginning of the course. In memory, that means workers which have the proper resources should be used with large memory, for instance, which then equally get quickly to a cost, right? Hence, to swipe the credit card again, of course, if you want to have an analyzing of streams in a very high performance. Hence, this is a model that basically you can do in different cloud vendors. I think by now, at the end of the course, you can imagine when there's some service in MS Azure around it with Spark, then we can basically do very similar things in AWS. That's already what I showed you many times in the lectures, where we had Hadoop, for instance, in the Elastic MapReduce service in Amazon, which is quite interesting also with MS Azure and the HD Insight cluster with Spark, very similar, maybe even being able to execute the same Python script on the streaming API on Spark. Enabling portability, maybe different costs of the resources, obviously, because here we're talking now about the hardware infrastructure by Amazon as opposed to MS Azure. So maybe the costs for resources are different and the costs for the service is different. But this is basically a very similar way of basically porting then applications via the Spark streaming API, which can be one of the benefits, right? And not running into a vendor lock. On the other end of the scale, where you have a very, let's say, very powerful streaming data service is Amazon Kinesis, but this is a very specific service, of course, used for real-time analytics, very stable, very powerful, but this is more or less a vendor lock. Once you decide on Amazon Kinesis and do your whole foundation basically on these services, you're kind of in this vendor lock. So like here in the Spark streaming API, where you can easily switch to MS Azure or even the Google Proc services, you kind of locked yourself into the Amazon specific services that you basically already learned. The SageMaker the same way a bit, although there you have at least notebooks which you maybe can transfer to other clouds. But here for streaming data, you really then have a vendor lock, which you here and there, of course, should try to avoid. But given the size of your company, chances are that you maybe want to stick with it, because these services could fill easily, again, a couple of lectures. Basically, if you go to Amazon and also the Amazon Academy and all the learning material, it has very powerful features from hashtag analysis that is basically then generating hashtag for everything that you have in terms of videos. So basically what I'm selling is really analyzing data streams already with a specific purpose that you don't really even have to program a lot anymore. So in Spark and in the idea of the filters that we described, of course, there the Python script is there, and you have to create your own Python script. Here we're talking about the full, more or less software as a service feature, where you can have your social media feeds, your videos, whatever it is, basically analyzed with the data streams of Kinesis, and then use it for different purposes. Of course, you want to combine it with some databases to really store, for instance, all the text or so in a specific Amazon database or so. But in the end, as you know from all the other Amazon services, it's basically something which is really neat and basically works together like a charm. Hence, big companies like Netflix, they just outsource all of this functionality and use Amazon Kinesis to really do the text analysis of the movies, to really also ensure that, of course, as Netflix has really commercial users, they swipe the credit cards, they need to rely on infrastructure that provides every time 24/7 almost services, right? So high reliability, high service uptime is for them of the greatest concerns. Otherwise, people will complain about Netflix, will stop their subscription, and so forth. And there are different data streams, data firehose, and so on. Is basically something where you have also from Twitter APIs, which then give you much more Twitter tips than the normal Twitter API, also a business model basically for this. So coming further basically on this Kinesis, you see, of course, the way how you handle now data. It could be something you had before on social media data, let's say a Twitter stream. You can also pick easily basically all sorts of inputs coming from videos. And here's just the example of a security camera, but of course could be a handheld device, could be other movie cameras, and you can really nicely work with this kind of streams of data and do some analysis, which of course then could be just the next input to something you want to combine with it. Let's say image recognition, right? As we said, Amazon recognition video services in order to understand what's happening in the scene. Amazon SageMaker, was you already know a little bit from your assignments, is a machine learning tool, so to speak, already ready to maybe do some machine learning with TensorFlow or MXNet. You can have different ideas how to work with these different video streams or combine them all, right? And this is, of course, something where Amazon, as you know already, is very, very powerful, offering a lot of different types of services, which are particularly tuned to also then work directly through the S3 storage again, or through other storages and databases directly with the other services you have basically in the Amazon portfolio. And here's an example how that works. Maybe if you just think about a kinesis stream coming in from a video observing cars, you want to have an analysis of the license plate, something you have right now probably around Groska, right? If you think about the parking downstairs, for instance, in -1 here in Groska, in our building, they basically have this idea of having your license plate, and from this you have the kind of kinesis stream as an example that then puts it to AI and will see, is this basically matching the license plate of people that really subscribed downstairs to basically have a parking place or not? And of course, then you can have other law enforcement parts, notified that this is someone parking wrongly, and then we get a ticket and things like that. So hence, it is very easy to create these things today in the cloud. But here you go, of course, the Kinesis service. Think about all the data as video streams coming in. You have to pay for all the storage. You have to pay for all the different, let's say, usage of the Amazon AI services, even let it be SageMaker and so forth. So a good business model again for Amazon, because over time you will accumulate data again and again, more and more. And as you know from previous lectures, as I said to you, getting data in is usually nice, but getting data out usually costs. And you can go on and go on. There are different ideas how to work with data streams, and then think about, again, you can analyze it maybe not with this, with the AI, but rather with the Spark on the Elastic MapReduce that we already know. So create your own Spark code that is then running on an EC2 cluster, load balanced, basically, and then have some output, maybe some visual analytics of the streaming data on the fly. If you use the Amazon Kinetics data analytics and statistics, which you can derive from that, or even if you have a real-time, let's say, tractor working on fields with some sensors that constantly sends data, of course, and then basically you use this data streams to really understand where all the tractors are actually working, how they actually work on fields, and see some actually output, or basically have already some sensors which say, maintenance might be in order. So proactive maintenance aspects that basically the replacement parts will be already ordered before you as the owner of a tractor maybe even know it, because the sensor already reported actually in a couple of kilometers, which we will probably reach today. We will have type of maintenance happening, so please send already the replacement part. A huge idea of data analytics called proactive maintenance, where we can easily spend 3 to 4 university lectures. Like wind wheels is a big topic in that context. It's incredibly costly to repair wind wheels and do maintenance, because usually you also here and there have to use a helicopter. So book helicopter time, have the replacement parts in place at the time when you book the helicopter. And on top of this, you need an expert being at the site at the wind wheel, in combination with the helicopter and hopefully the replacement part. So it's a huge scheduling exercise, which bears lots of money. And basically there you also find this type of proactive maintenance. But going further, just to provide you also an example here again, that of course, needless to say, you can find lots of them, of course, on the Amazon website, right? So how they use the Kinesis data streams, how it works in combination again with our famous S3 de facto standard, as we said, interface on Amazon, how we use, let's say, a service that is basically then using the search functionality, where you then can basically even search in the data that is created by Kinesis by providing then different services in combination of this particular one. And you see here in the film industry, this is also used, so to speak, to have different data pipelines looked at. And I don't go here in the details of this because I think you can imagine all of these different stories if you go to the Amazon Kinesis website, have real working applications. And basically, it's a tool which is very powerful and basically where you work with different parts of the Kinesis service. So it's not always the same one. You see that a little nicely here. Amazon Kinesis has different type of services that you even can combine with each other. So you don't have to choose with one kinetic data service, so you can actually use them one and one after another in a nice data pipeline that you already know a little bit from previous lectures. Data science pipelines are very important in practice, especially in business, to really have an ongoing production discipline that you always do. For instance, here looking at the click sites of webs, the websites and the click streams data, who is clicking which websites, and then, combining this with different data, processing this in real time, perform some data analytics, and then put this to basically different analytics, which really needs, let's say, the concrete analytics algorithms, but also have to scale in terms of computing, as you know, and then comes perhaps directly with some kind of personalized recommenders that you can imagine are now basically the ones that you also use in your assignment. And this in real time. Essentially, when you click, as you will know already on the Amazon Shopping website, you get a proper output in terms of personalized recommender. Now, connecting this back to the recommendation engines that you basically do in your assignments that we had also in 11.1 as a lecture. Finishing off a little bit with open source tools on that. Also here, we would have training to do for 1 or 2 university lectures. I just glimpse over them. There's Apache Flume as one proper open source tool that has the same idea of working with source and sinks and having a channel that could be maybe connected to a parallel file system or to the Hadoop distributed file system that you already know from earlier lecture. So basically it has a model that you can work. And in this channels, you actually have the possibility in these event data streams, again, to have the so-called interceptors, where you then basically, again, have the idea of the filter we discussed in order to analyze specific data. Is one basically in the stream, not a proper tweet or a tweet that basically we want to maybe mark as being whatever, basically things that are not related to your own channel in Twitter that you want to delete. And keeping track of that as a company can be quite challenging. So basically here you have an automatic way of organizing this stream, analyzing it, and with interceptors also act basically on that particular stream in case you find some tweet, for instance, which is malicious or so. And there's also the Apache Storm data stream tool that is relatively similar to basically the idea of Apache Hadoop. Again, it's designed by the idea of doing really distributed real-time analysis of these kind of streams. In a way you can scale up and scale down, as we already know also from Apache Spark. Of course, this is the Apache product, which is directly, again, so to speak, organized for streams. So it has some performance trade-offs, so to speak, to really being focused, of course, on streams enables you to focus on this particular part of data, but it's something which is also used in practice. You see here in many other players in combination with other things. As you know, Spotify was also using, for instance, S3 from Amazon. So you see, even the big players in the industry use very different services to fulfill the whole strategy of a product. Here you have Apache Flink, which is yet another of these different products where you have an in-memory technology example where, of course, the kind of role that memory can play is a very important one, because we know it's very fast. And if you see that we have more and more data growing, right, with 100 terabytes every day, 48 hours every minute, every day with YouTube, we basically going to a future where we basically have not really a chance to maybe store all the information. So there in real time looking within fast in-memory technologies at the streams is very important. They all have their different, let's say, ideas how they work. Of course, you have to think that some of these open source projects don't have really the perfect stability yet. So as they evolve over time, this is something, of course, from practice, you still have here and there also some hard time to really deploy them on your own. And here using clouds, which already done the business of deploying these, of already checking the quality, can help you, of course, in cloud products to do that. But of course, then you also have to pay for it and swipe the credit card instead of doing it on premise on your own resources. And then you can add this all to a bigger story where you think that you have different open source products, as I was alluding to in earlier lectures with the Hadoop ecosystem, of really then working and streaming in a very effective way. You see here an example where people also used basically a distributed streaming platform called Kafka, which is then used as a broker from very different, streams. And these distributed streams are then basically pulled together that you can then nicely analyze in combination with a Flink. So also this is an open source technology which is used quite often. And you see here a little bit the idea of why now Storm might be better versus in memory computing here, what we have in Storm and Flink, the kind of elements per second that you can really analyze with the number of CPUs and workers that you have is much higher. Obviously here you can imagine what that means. If you have an in-memory technology, you have to pay the price of really having a CPU deployed, which has then also big memory. Very similar like Apache Spark. So it's not a very fair game to say this, because basically here we talk also about lots of more costs. But sometimes, of course, the cost means something for the company. So maybe it is very important to have a high performant ratio here, because then also customers maybe are willing to have a very high price that you indirectly put to the customer if you're the cloud provider using the Flink system. So again, connecting again to previous lectures, as we heard, this in memory, very important, but you have to pay the price for it to have the right resources. Here's another connection to an earlier lecture with machine learning, a big topic we didn't touch called online learning. So what we had before was always essentially batch learning, or basically have all the data there, like our MNIST character recognition, like our Iris, Setosa, and Virginica we kickstarted the course with. So you train machine learning algorithm, evaluate the solution, launch it on the cloud with MS Azure, and basically it's can be automated process. And then you don't even need to update the data. In some cases, you just have it and then basically create more and more solutions for a perfect machine learning model. Now, in incremental learning and online learning, that's not so easy, bringing us back to the streams. So basically, they have a constant stream of data coming in. You have to chop it into different pieces. You learn from these pieces until that particular time step. You study the problem, you basically evaluate solution, and have the same loop, more or less, of creating a better machine learning algorithm, but it's trained online. So constantly are always data coming in, which differentiate this approach a little bit from what you have in typical learning scenarios. And of course, online learning would be, again, 2 university lectures. So here, again, just a pointer that, of course, this has also quite an active momentum these days. Continual learning, incremental learning, online learning are all on vogue topics today. But I think I stop here and think that's lots of material in the course, and these are just pointers. Let us summarize a little bit what data streaming means and why we have a big, let's say, increase in all of these different big data sources these days.
A key feature of environmental science is integration.
So what is EPOS? EPOS is a long-term integration plan. Earth science research allows the understanding of the physical processes controlling earthquakes, volcanic eruptions, unrest episodes, and tsunamis. EPOS is integrating existing research infrastructures and facilities. The key challenge is to open up the enormous wealth of available multidisciplinary data and promote cross-disciplinary science serving society.
EPOS can apply to different use cases.
EPOS will enable a step change in multidisciplinary scientific research and public outreach for earth sciences.
I think that's enough in this video. You have seen the idea of really combining now all these different data streams and data sets is, of course, a key challenge in this idea of big data, and perhaps one of the biggest challenges for the future, because it involves lots of different data types, lots of different experts. As you've seen, humans are still needed, right, to integrate all of this in a useful sense. And again, I think it's time to congratulate you. You basically passed the course with this video. Our last lecture 16 will be just basically summarizing some of the takeaway messages of the course from another perspective and grouping it a little bit in the bigger world around cloud computing, big data. And then we will talk a lot of different job descriptions next time, where you maybe have now a big chance of being, basically very good in some job interviews, because you have learned quite some important parts here in the course. So see you next time.